Welcome to an exciting topic, and this topic is adhesively bonded joints. And I welcome you to go through this material. I think it's very important for the design of aircraft, aerospace applications, and beyond. Here's a list of references that I have drawn upon to be able to communicate with you the approaches that are required in the design of adhesively bonded joints. So I welcome you to pause the video. You can read through these materials. You can find them and get knowledgeable about adhesively bonded joints, which is an important application in the design of aircraft and launch vehicles, spacecraft applications, and beyond. So why permanent joints? Why bonded joints? They do offer reduced weight. They provide great fatigue life. They tend to be damage tolerant to some extent. And there are stress concentrations in them, but not stress concentrations that will cause like a net section failure, as you will see in an open hole configuration of a plate. There are disadvantages in using these permanent connections. If you wanted to inspect, that can be an issue. And I'll be discussing some of that later. Bonded joints are also susceptible to environmental degradation. We will see later that there are going to be some difficulties in analyzing them, but we will address few ways that the industry has approached them. You require high quality control, and they are susceptible to workmanship issues during manufacturing. There's also the issue that you cannot disassemble if you wanted to, because now they're bonded. You could try to disassemble, but it's going to require tremendous amount of work to be able to rejoin the parts together. When we compare bonded joints to bolted joints, with bolted joints are easy to disassemble. You don't have thickness limitations. You're insensitive to this idea that we're going to see later with bonded joints, where you have feel and shear stresses involved. I mentioned here that they're environmentally insensitive. That is not quite right. There is some amount of environmental sensitivity, especially with composites. However, bonded joints do have slightly greater sensitivity to environments. We'll be showing you some data supporting that. You have a clear stress concentration that emanates from the hole itself and the hole elongation. In bolted joints, you add weight, yet again, you're adding a lot of weight, but you also have the issue of fatigue from the metallic components. You have poor bearing properties at times, and you can have fretting problems in metals. So bonded joints do offer an advantage, and the advantage is really the lightweight application of them. They improve the performance and durability, and you can bond several materials together. An added advantage is from the dynamic characteristics. It does have a natural way of reducing vibration because of its good damping characteristics. So again, bonded joints, it is a great technology that you can employ in your designs, but I will show you that when you employ this kind of technology, you have baggage that you're going to have to deal with. and we will talk about those baggages and the challenges that bonded joints can represent for us, that bolted joints do not have as much. So when you are trying to come up with the best design for you, I encourage you to think about whether going with a cool technology is warranted, because sometimes bonded joints, while they simplify things, can come with challenges along the road. Bolted joints, on the other hand, is a relatively straightforward approach, and it will have less baggage compared to bonded joints. But again, bonded joints does have its advantage, and people are highly considering this technology in their designs, and they're employed in our applications. There are two classical papers that I think anyone working in bonded joint designs should really study. And there's several one of them, but these are the two I would like you to consider to study. And these articles were published by a very famous um, person in this area. His name is Hart Smith, and he worked for McDonnell Douglas and consulted there as well. And I encourage you to read these two papers. So feel free to pause the video and find the papers right now, download them, and start to study some of the thoughts he had in this area. And I think he added really a lot of value in how we should approach bonded joint designs. The applications for bonded joint designs go from aircraft to stiffening elements, cylindrical structures where you don't want to use a bolt. We've seen it in drive shaft and fittings, and again, you can find this type of applications in an aircraft type application where you have two panels. Okay, two panels are subject to significant amount of loading in every direction, highly complex. And then you have this splice. This panel here in yellow connects the two sides with a bond. And I'll show you later cross sections of these kinds of bonded joints, but they are used in applications to, again, reduce weight. Here I am showing you various joint configurations. The most used, or one of the ones that's used, is a single lap joint. And you will see this quite a bit. And I'll discuss some of the disadvantages of a single lap joint. You have tapered single lap joints aimed at modifications to the single lap joint to try to reduce the stress concentration. I'll go into that a little more later during the discussions of design best practices. We also have the single strap lap joint. In this situation, you have a splice that connects the two sides of the panels with an adhesive joint. And then you have a double lap joint. The double lap joint provides adhesion on two sides, and the double tapered strap joint provides very similar application to a single strap lap joint, but on two sides. And it's a modification of the double strap lap joint. And this one is intended to decrease the stress concentrations as well. A good design for a bonded joint, while it's very difficult to achieve, is to fail the joint, is to fail outside of the joint. We don't want to fail within the joint because of the complications or the failure modes are present, and due to the environmental sensitivity, if you can design the joint to fail outside, then you're going to have a very robust design. However, to achieve that, it is quite difficult. It's quite challenging. On the right side, I show you various other types of joints, and I want to raise your attention to the stepped lap joint and the scarf lap joint, scarf joint. These two joints are also very effective, and I'll be showing later how these different joints are rated against each other. Now, because one of the things I'll be discussing later is that when you select a joint, while some joints may be preferred in terms of strength relative to another, there's potential difficulties with the manufacturing process, which may make you go with a more lean design. It may make you go with a easier to implement design. And so for that, from that perspective, it's important to really evaluate when you went from bolted joint to bonded joint, did I really save weight? And so feel free to pause the video and think about what is the load path when you compare all these different joints. And it is worth thinking about it because it becomes handy later as we discuss bonded joints. As an example, when I load up the single lap joint, I will load up along this bottom adherent. The top adherent is also loaded actually, but you have this eccentricity. So it's causing a bending component to it. While you look at this double lap joint, you have very little of that. So think of that as we move along. So there are different types of bonding. We have secondary bonding and co-bonding. Secondary bonding, you're looking at bonding two or more pre-cured composite parts with adhesive, where only chemical or thermal reaction occurs within the adhesive itself. Okay, so that's an important consideration. You have to prepare each cured substrate carefully, and you want to be able to be cognizant that reheating previously cured substrates can sometimes be a problem. Then you have the idea of co-bonding. The idea there is that you're curing two or more elements that can include the composite. Maybe one of the adherents is partially cured, that's okay. Or fully cured. But the idea is that you're curing all these things together to completion. And you're doing that together in one step. You have to be careful with the surface preparation. Otherwise, you may have an issue. This is true for almost all the adhesively bonded joints that we'll be discussing, configurations, but particularly important for co-bonding. Metal bonding is the same as secondary bonding, except the substrates we're talking about here are metal instead of composites. Metals can be bonded to composite, but I want to raise your attention that coefficient of thermal expansion can be a problem. Okay, so if you have an aluminum that has a coefficient of thermal expansion, that could be significant. And the adhesive also has a coefficient of thermal expansion. If I were to bond this aluminum with a composite, which coefficient of thermal expansion is quite small, then the delta temperature is going to cause a greater stress in a configuration of that nature. So you may want to move to metal that does not have a coefficient of thermal expansion that's as high. Invar is such material. However, you have to balance the expense, the cost, the weight. All these considerations should be thought about in the application of interest. So keep that in mind. We can't bond metals to composites. Just keep in the back of your mind, in the designs that you're working on, that the discrepancy in the coefficient of thermal expansion, the difference in stiffness, can cause other issues that should be considered. And so perhaps a bolted design may have been just fine, Again, make sure that from the system level perspective, if there's no weight impact, that you may want to consider bolted design. There's nothing wrong with a bolted design. But moving to a bonded design will produce new challenges that you have to deal with, and you have to knock each of these challenges down to be able to be successful at using them. And I'm not advocating against the use of adhesively bonded joints. I am warning you and cautioning you that it comes with a lot of work, and it requires careful attention. Metals require a tremendous amount of surface preparation, including the application of corrosion inhibiting primers prior to bonding. That's an important consideration for long-term durability. And you want to make sure that when you're bonding metal to carbon, that you account for the potential of galvanic corrosion. Okay. Typically, at the bottom, I show you a figure that explains the kinds of things that we need to consider. You want to have the correct mix and apply the correct adhesive. You want to properly cure the adhesive. You want to control the bond line thickness, because I'm going to show you later evidence that if you don't control the bond line thickness, you could have significant excess adhesive thickness, which can now potentially decrease the overall strength. Potentially could expose voids now. And then I should have started saying that you want to prepare the substrates of the surfaces well prior to bonding. And that is something that needs to be considered, okay? And so I also want to point out the importance of sometimes including a clamping pressure to try to get all the bubbles out, all the voids out. And that's something that people do work on to try to address. So I'll continue going through the types of adhesives that you could have. And there's many. You have adhesive types that depend on chemistry, form, type, or load carrying capability. From the load carrying capability perspective, you could have structural adhesive, semi-structural adhesive, and adhesive that's not really intended to be structural. It's there for cosmetic, or it's intended to prevent further damage. Okay, and that cosmetic can also play that role, so it's important to also consider it. And then you have forms of adhesive. They can be in terms of paste, liquid, film, pellets, tape. And so it's important to understand that in a design, you want to be able to make decisions relative to what you really need for your application. For structural adhesives, they tend to be strong adhesives, and you want to use them below the glass transition temperature, because if you go below that glass transition temperature, you're going to degrade the polymeric links in a significant way. Okay, and so it's important to consider that there are various types of adhesives, including epoxies, cyanoacrylates, urethanes, and acrylics. But overall, the structural adhesives can carry significant load, and they can lend themselves to structural applications, okay? And just to put it in perspective, some of these bonded joints, if I were to have a bonded joint, it's possible to have a bonded joint that's about 1 inch wide or 2 inches wide, and it could carry upwards of 2,000 to 3,000 pounds for every 1 inch wide. So it can be quite significant amount of load they can transmit through these joints. Liquids is one form that adhesives can come in. The viscosity obviously is such that it's liquidy form. It works best in thinner bond lines and provides great and higher degree of direct load transfer than pastes. And the thickness range can be between 2 mils all the way to 10 mils. However, liquids tend to be more brittle and less resistant to peel loads than other pastes or films. Often liquid adhesives are categorized as paste without distinction, which I think is a mistake. I think there should be some amount of separation between the two so people know what we're really talking about here. Paste have higher viscosities and they generally work better with slightly thicker bond lines, although I will show you later if you go too thick, you start to impact that strength capability. The thickness range can go from 5 mils to 20 mils. Again, controlling that thickness can be quite important. Film adhesives are tremendously used and they work well, but they need to be stored and frozen. There's an out time associated with them. You have to thaw them to room temperature before use, and they require an elevated temperature cure cycle. And it is important to understand that these are quite used in our industry, but they can present some problems, especially when you have adherents that are not tightly controlled in terms of the dimensional tolerances. Film adhesives can now be subject to little more difficult time to bring those adherents together to work together, and so that's why you want to know when to use them. Film adhesives can be used significantly in the honeycomb type structures or sandwich structures. Um, and they're using many other types of applications. FM300 is an example of that. AF191 is another example. And we can go on and on and on. But I invite you to pause the video. It is worth to maybe go through vendor data and look at the different companies that exist that provide these types of adhesives. So welcome back from your pause. I hope that you're making this into an interactive experience so that you're not just listening to what I have to say, but you're bouncing back and forth between the materials presented today and what you're finding from the literature. I think there's a lot of value to getting a full immersed 8D audio experience, if you will. Some structural adhesives, such as epoxies, they have a wide range of high strength adhesives with a variety of curing and surface temperature profiles. A common adhesive that you're going to find online quite a bit. So the Hysol EA9394, there's versions of that. So you really want to dive in and understand the limitations of each variant because each of those can work for different service environments. And the cool thing is that while they can service at high temperatures, and not too high, by the way, but it can be quite high, 180, 170. You need to have, you can do this at a room temperature cure, and that's a huge benefit. Vacuum bagging is a common thing to use. Mixing becomes important, obviously, epoxy, but it does eliminate gaps between composite surfaces. That's a neat thing about it because composite surfaces that have the waviness on the surface and this Hysol 9394 can get into those crevices and offer great high strength properties. It's important to consider epoxies as a great way of bonding dissimilar structures that perhaps the dimensional tolerances cannot be controlled as well, but it can provide great strength. We have the BMIs that can go up to 600 degrees F, and the cyanide esters tend to be great because of their low thermal coefficient of thermal expansion. So just want to bring that to light because there are various types of composites that can be considered. I borrowed this particular slide from one of the sources in the second slide of this briefing. So I welcome you to go back and kind of find those sources. I think you'll be successful in finding them. But this particular source, I thought was really good because it shows you the kinds of things that can go wrong. Here, what you're seeing is something called a fishbone diagram. But I'm not going to discuss what a fishbone diagram really is. My goal here today is to really discuss the things that can go wrong. You can have a composite fabrication issue, a material supplier issue, or quality assurance issue, a mixing issue, or training issue. All these things can influence the a premature failure of an adhesively bonded joint. You can have poor work instructions. You could have the surface prep not being as the one you should have followed, or attention was not put in, or gloves were not used. There's grease or some contaminants of concern. You could have the expiration date of the adhesive. You can have cure times of the adhesive being incorrect, or vacuum limits that are exceeded. Mixing methods are incorrect. The adhesive was not properly applied to the full surface, the full bonding surface. The thickness was not controlled. And I don't want to keep boring you, but I think it's important to keep all these things in mind. And when you go into a failure investigation, you can borrow this right away and start studying what could have gone wrong with your particular application. And not just the people and the method can go wrong, but you could have issues with equipment and the vacuum gauges and the heaters and so forth. The material itself could be a problem. The 3M material, the solvents used, any of these things can introduce new variables into a problem, into a premature failure. You have environments that need to be considered. Perhaps you didn't have the proper storage environments for the various constituents. You had the incorrect exposure of these adhesively bonded joints to potentially higher temperatures than the structure could see that was designed for. And so it's important to consider, ensuring that when I say environments, that your shop is clean. Because say you have paint in the ceiling, that paint in the ceiling, those chips can fall into your structures. You want to pay attention to everything when it comes to bonded joints, because any of these things can cause a significant amount of degradation in strength. And it doesn't have to be significant. It can be a small amount, but sufficient enough where your design is a peril, okay? Further, you have measurements, system could be off. So notice here how I didn't even talk about design. The design itself could be not a good one. And I didn't bring that up here because that is a common issue, is that you have a design error, and which was validated through subscale testing. That was not the best one for your application. So test like a fly, as we've discussed previously in the previous lectures. Those things are important. But notice how many of these things that are subtle can impact the ability of the strength, the ability of the bonded joint to sustain the strength for what you designed it for. It doesn't matter how good you design a joint. If you have a problem in any of these areas, it can impact the ability to have that joint to perform as intended. So I hope that's very clear to you, and that you take some time thinking about the things that you need to pay attention in the design of these joints. And that does not just, the design of a joint does not just end in a computer. You want to follow that through the manufacturing floor, the training, making sure the equipment is properly calibrated, that the storage environments are proper, that the materials are not expired, that the out time is correct, so all these things need to be considered, and keeping contaminants away as much as you can, okay? So sorry for going too deep into this, but I think it's fairly important to understand that we can do the best analysis in the world, but then yet you could have an issue with the application of this design in the field. So there are other issues that we can keep going on, but this one, the way I'm showing it here, is in the context of a failure investigation, and this one here is called a fall tree. It looks like a tree. Um, and I show this mostly as a different way of showing you that the same types of things we talked about will show up here. One that I did not talk about is the adhesive being too thick or thin. It was kind of covered when I talked about glass beads and things like that, but adhesive controls and things like that. But this approach works well as well, a fall tree. I'm not going to use the time today to discuss whether a fall tree or fishbone is preferable. I'd rather keep a big picture perspective and ask you that when you work a failure investigation dealing with adhesively bonded joints, you really want to dive into every area that could have caused this failure, whether it's a fishbone or fall tree. I don't care. Just get down to the bottom of it and try to determine what really happened. And what I'm trying to tell you is, if I had a bolted joint design, the fall tree and the fishbone may look a little bit simpler because all the subtle things I wanted to keep in mind, all the knowledge that has been passed from the investigation needs to be considered. Okay, we have incompatible materials coming together, inadequate process controls. We have contaminated contaminated surfaces, and the way these defects can show up in adhesives is porosity is one. These bonds that are clearly occurring. You have voids, poor cure, poor mixing, cracks. Some of these things you may not be able to pick up through an ultrasound inspection, a non-destructive evaluation where you send the sound from one end, hoping that the sound goes all the way through in a uniform manner and comes back with no evidence of a problem. But if you have a defect, then the sound goes through, bounces back too quickly, so you know something's going on there that should be examined. If you have a situation where you have a weak bond, so a poor cure area, is possible. So pretend this blue here is an area of poor cure, but there's not a clear D-bond. It's possible for the sound to go through, come back, and you may not know that you have a problem. So weak bond is a danger in these adhesively bonded joints. And how you address that, how you determine whether an adhesively bonded joint that has weak bonds is not a problem. That is a challenge. That is possibly the biggest challenge of designs using this technique, this employing this type of joint. These issues are more emphasized for paste than film adhesives, and so that's very important to consider. What are the failure modes you may see in bonded joints? And I bring that up because it is going to show you the types of failure types that you could have in this type of joints. You can have an adhering joint. That is my preferred. Fail outside of the joint. Don't be too sensitive to what's going on within the joint. A cohesive failure occurs within the adhesive. An interfacial failure or adhesive failure, which is the failure between the adhesive and the adherent, can be quite scary. It may point to a contamination problem at the surface. An adherent failure is a failure in the composite, so away from, we could consider this outside of the joint as well, and we could consider this a somewhat of a preferred failure too. Although we don't want to have this, we want to have this. But let's be realistic. This is the type of failure you will see when you have composites. And if you have this type of failure, I get a little bit happier because I don't have it right at the adhesive. Now, to predict this kind of failure is not easy, but it's not as complex as having it right at the joint, because I'll show you later that predicting failure of a joint is not easy. You have the cohesive failure due to peel. This one was due to shear. But in general, these two are in the same bucket, these two are in the same bucket, these two are in the same bucket, and I really prefer this one. If we can get to failure outside of the joint, that is the preferred approach. Again, that's not, that can be impractical to get there. Okay. Now, if you compare this to the failure modes in a bolted joint design, which was previously covered, in a bolted joint design, you're looking at bearing failure, net section failure, shear out failure. And I feel a little more confident about being able to predict those. I know you still have complexities if you use composites, because, hey, what is the stress concentration factor and how you account for the preload and all this other stuff? There are complications there. They are unique to bolted joint designs. But with adhesively bonded joint designs, these are the failure modes, but they're quite more sensitive to things that can go wrong in the manufacturing floor. Actually, all the way from the supplier transporting the materials all the way to the manufacturing floor, the storage facilities, and so forth. So all that stuff needs to be really cared about. And these, again, expressing my desire to failing outside of the joint. So it's a repetitive picture from a different briefing package, whose reference is in page number 2 of this YouTube video. Why don't take a few minutes and go to Google and type adhesively bonded joint failures, okay? And click images now and see what you find. And if you don't find as much, maybe type shear failure, peel failure, type contamination. See what kinds of failures you could have. And secondly, I invite you to look for microscopy data, looking for this voice that we talked about, and the connection of damage or defects, pre-existing defects within the joint, and the ability of the non-destructive evaluation techniques such as ultrasound being able to pick up these types of damage, okay? I won't be able to cover all those today, but I think it's worth it for you to pause the video, do a little bit more research, instead of getting tired listening to me. I think there is some value in doing that. So let me go ahead and pause the video at this moment. I want to resume going here through, welcome back if you did do that. And if you did do that, I congratulate you for being the king of bonded joint failure mode expert, which if you have that title, is a big deal. So adhesively bonded joints will fail in many different ways, like I discussed. Interfacial failure occurs when you have failure within the adhesiveness and the substrate, as I discussed earlier, and that's primarily due to the lack of chemical bonding between the adherent and the substrate itself. And that indicates a potential issue with the surface preparation, contamination, or an issue with the adhesive itself. Maybe it was expired, maybe the out time was too long, whatever it is, it starts pointing to something interesting that should be looked at. If you have cohesive failure, if you're gonna fail within the joint, that's not a bad failure to have. It's failure within the adhesive, but that's good. It's good if you failed it at the lows that you thought you're gonna get. But if you have a joint that fails at lows that are significantly lower, that points to a cure problem, or moisture issue or contamination issue within the adhesive or pure mixing issue, a poor mixing issue as well. A substrate failure usually occurs with composites. If it was a metal, it's less likely. Actually, almost not likely at all. But if it's composites, you're going to have interlaminar fracture sometimes away from the adhesive itself. Okay, so that's pointing more towards this type of failure mode here to the top right. And usually that failure is going to happen between the first and second ply, but not necessarily. It can go a little bit deeper, adjacent to the bond line, and that is a tough one to control, but it is not a bad failure mode to have because it tells you you're relatively insensitive to what is going on in terms of workmanship sensitivity at the adhesive itself. Okay, so that's not too bad. Now is these are difficult to predict, and sometimes you want to use analysis tools to guide your design. But when it comes to bonded joints, we really want to validate their performance through coupon level testing, subcomponent level testing, and so forth. And I'll get back to that later to ensure that's clear to you. So surface preparation of composites is extremely important. There's a lot of different ways to approach it. Abrading the surfaces to increase that connection between the adhesive and the adherent. You have the grid blast approach. It is a high-risk method. We want to be able to remove dust and debris from the bonding surfaces without inducing contamination. And that is achieved with solvent wipe, with approved wipes, but making sure you pick up any contaminants. But that now becomes an issue now from the moisture perspective. Am I introducing moisture into the porous composite surface? So an alternative is to use a dry wipe or approved wipes, but you may want to wipe sufficiently enough where you're confident that all contaminants have been removed, the dust particles have been removed. And the thing I want to point out here is that if I ask manufacturer A to design a joint and manufacturer B to design a joint, and I ask two people to go and put those joints together, but they're different people with different training, I will suspect that the two failure loads you will get from the two different designs or the manufacturing that came out is going to be different. Okay, so it's important that whatever method you're using, you're consistent throughout your qualification program, because the surface preparation technique you use today is going to impact later on what you do. So if you're going to later change your surface preparation technique, come back, requalify, and make sure that you haven't changed the strength capability because of something you changed in your processes. As good as surface preparation is, as good your FOD control plan needs to be. If you have FOD in your manufacturing facility, if the air is not clean, you can clean all you want, but you're going to have particles descending back into those surfaces. There will be times where you're working on other tasks associated with the surface preparation that will require your attention. And I've bonded stuff in graduate school and even at the company I work for, you know, and I recall like spending some time, you put the film adhesive down, and then you start working on other things, and you come back to it. And there are things that could happen in between, okay? So that we need to be cognizant that those could happen. If you go to a composites facility, I've gone to many in the United States, you're gonna see sometimes they have bags, they're attached to the ceiling so that any paint chips don't fall into the structure you're trying to manufacture. I've also seen safety nets of basically some bags that are above the area you're working to pick up any type of um, issues. I've also seen fans pointed in the other direction to prevent any new particles coming back in. Again, the work environment is as equally as important as cleaning the surfaces. To achieve an optimum bond with metals, clean the surfaces, dirt, refresh the oxide layer with a suitable process, chemically etch or couple to fresh oxide layer, apply a corrosion inhibiting primer, uh, and use appropriate adhesive for the application. And then you want to provide a uniform bond line thickness as much as you can so that you are distributing that stress uniformly. Okay, that's of extreme importance. You want to provide a constant clamping pressure, and then you want to cure the adhesive to achieve structural properties that you desire. To achieve a optimum bond with composites, you want to energize those surfaces, clean the surfaces, use appropriate adhesive, and again, uniform bond application for achieving uniform stress as much as you can, and provide that clamping pressure needed to remove any of those internal voids. You know, the hope is that as you're applying that clamping pressure, that these voids are getting out. Okay, of extreme importance in adhesively bonded joints. And in summary, this is a summary, not a summary of the whole course, because we're still probably 25% done. But optimal structural performance of bonded joints is achieved by requiring that preparation of bonded surfaces, eliminating contaminants, restricting the environment by control of the storage environment, but also restricting, um, you know, particulates that could be occurring in your facility, limiting bonded agents to their qualified life, controlling the curing processes. Inadequacy of any of these steps, in summary, can cause issues in your bonded joint. And it can go unnoticed until it's too late, and it could be an issue. High humidity at the time of bonding can cause significant strength loss due to porosity. Very important to understand that. FM 300 has been proven that at 86 degrees F, 4 hours exposure can result in microvoids. It can reduce up to 53% of the peel strength due to humidity exposure. NDI will have very difficult time finding this porosity. You can try looking for those defects, and you may not know we have basically a bomb waiting to explode, you know. And so it's important to pay attention to these subtleties, in that the certification of your bonded joint be really anchored to the processes you have in place. And that also includes to controlling humidity in the environment you're working on. So we have a lot of areas here to think about: environments, materials, controlling things like tolerances, the machines, the methods, the people, the training. All those things can impact the ability of the bonded joint to do its job as you had intended it in the first place. So typical vendor data you're going to get is ultimate strength, thickness, strain, modulus. And here's a comparison of some of them so you can kind of see for yourself. Comparison will be FM 300 with FM 73. And so it comes handy kind of looking at that. Now, the impacts to the adhesive strength go beyond what's going on in the lab environment or the manufacturing environment, but you do have the post-bond moisture issues. You have hygrothermal effects that could be a problem. You have temperature, you have UV radiation can be a problem, not necessarily all the time. You have water ingestion. Any of these things can exacerbate the problem. There are not only limited to what occurs in the manufacturing lab, but beyond that environment where you're exposing that joint to the environment that's going to service. And I didn't even cover that here, but say you have a joint, and a joint could be, say, like the one of the aircraft I showed. And so perhaps now I have an impact damage event where you have a tool that drops right where the splice is. I know it's like very coincidental, but don't rule it out. And so, especially with that, when that part is kind of protruding a little bit, you never know. You have some amount of impact damage that occurs. Can you actually see that? And that complicates things quite a bit. Now, geez, you may say, well, wow, the number of issues that can go wrong are quite painful. Should I use bonded joints? So I'm not saying don't use them, but evaluate for your company, for your application. Does it make sense? It's going to come with all this baggage. Does it make sense? And if it comes with this baggage, do I have everything in place so that I can have a good joint for use in service? Okay. I want to show really quickly the effects of the hot, wet conditions for constant bond line thickness. Quickly, you can see the drop from cold temperatures, room temperature, all the way to elevated temperature dry, elevated temperature wet. And now when I start getting past the TG, significant drop beyond that. So here's how it can impact the shear strength of a joint. And another picture illustrating that the stress strain curve even changes. So with metals, in some composites, you're used to the stress strain curve not changing very much for this temperature range that we're talking about. But with bonded joints, as you increase the temperature, now you could even introduce even more bending at the joint. But maybe you have more ductility, so it kind of cancels out the potential for damage. So it's very important to understand that adhesively bonded joints, even the stress strain curve of these materials is greatly impacted from brittle all the way to ductile. Okay, and not all of them will, not all the adhesives are going to have this behavior, this exact same behavior, but there is a good chunk of the adhesives that do act in that way. So that's something to really understand. The effects of hot, wet conditions can be quite significant. And here, what I'm showing you is that for various thickness changes, so here I have 15 mils, 80 mils, and 160 mils. And this comes from one of the references in slide number 2 of this package. I invite you to download that, study what they're talking about relative to this figure. But here, what I want to do is simplify the message. At cold temperatures, notice how the performance was dropped relative to room temperature, potentially due to the brittle condition at cold temperature. And you can see that for 2 thicknesses, 3 thicknesses for this particular PTM and W adhesive. And then as you go hotter, you start seeing that drop due to the temperature environments that these things have exhibited. Another point I want to make is you can see here quickly that the thinner the adhesive, the better in general. You can see that a trend across all the environments. So that's something I'm going to come back later and even emphasize further. Okay. So yeah, so let's discuss a little bit about test methods that are used. I'm not going to go and discuss each of these in great detail because I think you can go to YouTube video or even download the ASTM standards for each of these. And in fact, why don't pause the video, look at these ASTM standards, these ISO standards, and go ahead and download it. You can get that through your university or even the company you work for. Uh, and I know that you'll be able to do so. But if you're looking at uh, how to measure mechanical properties such as tensile strength and modulus, the tensile butt joint does a great job. You could have some additional stress concentration coming from the idea that you have the similar materials coming together. The T-peel test tends to be a successful test to get peel strength data, kind of connected a little bit to fracture. I'll talk about that later. You also have the climbing drum method, the floating roller method, and you can look at typical specimen dimensions, materials suitable for testing, and fatigue performance, like which of these is suitable for that. Environmental suitability, and these two tend to be quite suitable for trying to determine how the environments could impact the strength. And then the very last row shows you the standard test methods available. I also invite you to look at the shear test methods, which at least for the double lap joint tends to be a lot more connected. The single lap joint provides shear strength, although I'll show you later that the single lap joint can have some issues if you think you're really getting shear strength. But it does give you information. So you don't want to ignore it. It does give you information. Here's the typical dimensions for the samples. You have the V-notch, beam, and the Arcan test. These tests are targeted to understanding the adhesive behavior in itself. Okay, for the Arcan method, we have no standard method. For the V-notch, we do have it, but not for the adhesive itself. We have it for the PMC, but it has been applied to the adhesive directly. They're also very suitable for environmental studies. The creep test in the single lap does a better job. The double lap does also a very good job. Fatigue performance, you know, the single lap and the double lap both do just fine. When I say limited, it's just that you could have some issues, but the real issues are coming from the peel, and I'll discuss that when it comes to single lap. Is that you're really getting a peel component to things here. They're getting kind of ignored when we say shear test methods. So that's why you want to keep that in mind. Is that when I say shear test methods, do not think you're not, you know, you're getting, you know, nothing other than shear. You're getting some peel. And so we have two lap joint standards that are used in industry. The first one is called the standard method of test for strength properties of the adhesive in shear by tension loadings. And this one is commonly used for metal to metal type configurations. The geometries are given here, and I invite you to again pause the video, download the ASTM standard, and kind of read through to understand what that test is about. And then we also have the strength properties of adhesives in shear by tension loading of laminated assemblies. And you will see here that there are some additional changes that was done to this sample to mitigate eccentricity and prevent any type of first ply failure, although sometimes you can get them. And so I again ask you to pause the video, download these two standards side by side, compare them, study them, and I think we'll get a lot out of them. We also have another standard, and I invite you to go to this link. It's a great link, but it's a D5656, and it's a thick adherent test. So the adherents are fairly thick, and they intended to be thick to really measure the stress strain behavior of the adhesive, and you know that's a goal there. You'll see that in all these tests, if the bond line is not controlled, the thickness, you're going to get a different behavior in the stress strain curve. For example, here you have various thicknesses, the effects of various thicknesses, and the stress strain curve is all over the place. Very similarly, with this test, you could be sensitive to surface preparation and all that stuff I discussed before. So it's important that when you're getting these properties, you be consistent to what you plan to do for the design. If there's a disconnect, then we start having some issues with what we're trying to achieve. There's also the fracture testing, the mode 1 fracture testing. But before I go to this, I want to make a comment. So these testings are really intended to target the strength properties of the adhesive. So if you have a different configuration, I'll show you later, but I want to see some sort of subcomponent level test that takes me from this coupon level test to the actual application without having to go to full scale yet. And so you don't want to jump to manufacturing a whole aircraft with a joint to only find out that you spent millions of dollars for something that's not going to work. I'll be covering that point a little bit later. Okay, so let me move to fracture a little bit. And fracture testing plays a big role in the analysis of adhesively bonded joints, especially if you want to look at the idea of how strong these joints are to flaws within the adhesive. And so we do have 4 types of tests that can be considered. One is called the wedge cleavage, the compact tension, the double cantilever beam, and the tapered double cantilever beam. So 4 different tests. We suggest you don't need a high quantity of specimens for the double cantilever beam, but you do require them for the tapered kind. There's some scatter that goes along with the tapered kind, the tapered double cantilever beam, which is shown here in the bottom left. The specimens are provided here, but I think what is important here is all of them are great and suitable for environmental, to quantify the environmental effects. So that's great. The fatigue performance has been used successfully for the compact tension, the double cantilever beam, and the tapered double cantilever beam. And the ASTM standards are provided here at the bottom. And again, I invite you to pause the video, force yourself to download these ASTMs. And I know you probably have over 40 now from all the ones I told you to download, but at least you have them handy. And you can start studying them anytime you have a downtime. And I think it's very helpful to see the subtleties in the preparation of all the samples, because this translates to what we're trying to do with making the designs robust. We also have a mode 2 testing. So mode 1 is an opening type mode, which is mode 1 is basically pulling the top and bottom so that the crack tip is in an opening state. So you're opening the crack tip. Similar to when you peel a banana, that peel, as you pull it away from the banana, the core of the banana, that's opening, okay? A mode 2 test can be described as, say you have a very thick phone book, although those have been, we don't have those anymore. But find an old phone book or old Mac Master, one of those very thick, flexible books. And if you were to bend that very flexible book, you're going to see that every page slides relative to each other fairly easily. The mode 2 test is really trying to understand the performance in the sliding mode. So if you have an adherent at the top, adherent at the bottom, and there's an adhesive right in between, I'm trying to understand the resistance of that top arm, the top adherent, relative to the bottom adherent when I'm subjecting the structure into a shear loading, so that the top arm is relatively deforming to the bottom arm in a way that you get shear at the crack tip. So you don't get as much crack tip opening like in mode 1, but you get the idea of trying to shear the adhesive in a way that it cracks it. And so the mode 2 component is trying to target that. There's 4 types of tests for this fracture test. There's the thick adherent test, the torsion butt joint test, the napkin ring test, and the ENF test. And so these are the ASTM standards that go along with them. And they're all great for environmental studies, to study the effects of environments such as temperature, moisture on the fracture properties. We also have some of the specimens dimensions provided. You don't need a huge, I recommend a larger quantity of samples, but the scatter is going to be significant. And so, but what you're going to find often is that the mode 2 fracture toughness will be at least twice of that of mode 1 when you're working with adhesives. So that's something to really keep in mind as you go through this exercise, as you go through all this stuff. I also want to point out a typical test matrix. What does a typical test matrix look like for characterizing the properties of an adhesive? So this particular picture came from one of the FAA references in slide number 2. And here what you see is that they're evaluating the nominal bound line thickness. And then we're also looking at number of replicates per condition, where CTD is cold temperature dry, room temperature dry, elevated temperature dry, elevated temperature wet. And these are the conditions that could be recommended for testing in order to get a good statistical understanding of what is going on with the properties. Okay, if I were to do a test program like that, I'm looking at 180 samples just by doing that. And just keep in mind that I could have various joint configurations, and this doesn't really encompass everything I really want to have. Okay, so we want to have a substantial number of tests to really gain confidence in the properties that perhaps will be used in the analysis. Okay, my goal is to get that understanding now before I hit the full-scale test. So I don't fail that full-scale test, I have to start over. That'll be a problem. I want to gain the understanding now. If I can correlate finite element models of these coupons, why not? Start here and then complicate the problem as you go up. So the test temperatures are typically have a range to them, plus minus 5 degrees. You're looking at relative humidities and exposures in the order of 1,000 hours. But the idea is really to fabricate, the samples and maintain them in a controlled environment. You want to do that for sure. So let me pose a design challenge for you. Okay, I already gave you the answer in this chart. I recognize that, but why don't think about this for a minute? I have a single lap joint and I apply a load of 3,000 pounds that gets reacted by the other adherent. So intuition says that if this is a 1-inch wide coupon and the overlap length is ½ inch, perhaps the shear strength for this lap joint is 6,000 psi. So it's a very simple calculation: 3,000 P, and the area is 1 times a half. Okay, I get 6,000 psi. All right. My question is, what happens if I make the overlap of this longer? Okay. Will the failure load be? Now I calculated tau from the first situation, 6,000 psi strength. I have it there. The area for the second situation, still 1 inch wide, but I made the overlap twice the length. I get a failure load of 6,000 pounds using this simple formula. But I have bad news for you. This average shear stress design methodology is fundamentally flawed. And why is that? Why is that? If you go to Hart-Smith, there's a reference, there's a paper that goes into, hey, the lap shear coupon is useful for quality assurance, but be careful for using that because it's misleading for design data. Why is that? This is not true. If I take the overlap and increase it by twice, I don't get twice the load, unfortunately. And the reason is because when you look at the stress distribution, okay, along the overlap, and I call this the overlap, the location where the two adherents are overlapping. That's why it's called overlap, okay? If I look at the peel stress, which is the stress up and down, okay, in the y direction, the peel stress, and I look at the shear stress in that adhesive, you're gonna find a peaks at the edges of the sample. In fact, using some of the closed form solutions, you will find that this reentrant corner, and this reentrant corner represents a stress singularity. So for linear elastic materials, this stress shoots up to infinity, okay? And so you could decrease the strength of the singularity by using elastic plastic type analysis. But the point I'm trying to make is that the behavior is really driven by what's going on at the edge. In the middle, you're not getting a lot of action. As you can see, it's fairly low. The peel stress is almost zero. In fact, goes negative. You have some amount that goes negative in compression, which is a little bit confusing. But if you look at what goes on, that's really what happens. It goes from tension to compression, and then to a very low value towards the center of the sample. That's what happens to peel. While the shear maintains some amount above a certain amount, but then you have some peaking going on at the edges. So the question is, how can you even design a joint that behaves like this? And that is the fundamental challenge in the design of bonded joints. And that's what makes it so complex. So not only you have to pay attention to the subtleties in the manufacturing and the environment that the joint will be exposed to, you also have to pay attention to how to even design a joint that appears to be very simple, but yet so complex in terms of what is required to design them. Now let's look at this because I think it's extremely important to look at this. So you have an overlap joint. The question is, as increase the overlap length, is the stress peaks at the edges dropping? The answer is yes, it's dropping. But it's not like you're getting a huge benefit. Look at the 25mm overlap compared to the 15mm overlap. What you see there is, well, I decrease the overlap length by a lot, or I increase the overlap length by a lot, the shear stress has not dropped by a lot. So it's not a one-to-one. And I want to point out that for a single lap joint, that's what you see. In a double lap joint, things are even more weird. As I increase the overlap length, the shear and the peel are relatively constant. So that overlap length is not really helping me decrease a peaking that occurs at the edge. And if failure is driven by peaking at the edge, we have a problem here. I cannot make that joint infinitely long, and I'm not getting a lot of benefit. So what is our optimal overlap length? That's the question we have to ask ourselves. So as you saw, there's a lot of challenges here. And let me pause the video at the moment. I want you to pause the video in a moment and really immerse yourself in this experience so you understand what we're talking about here. We're not talking about a simple problem where you can design a bonded joint with your eyes closed. There are things we can do, best practices to really get a joint that works out. Some people contend that by, if you can figure out the average stress of 6,000, perhaps don't design it to 6,000 if the strength is that much on average. Design it so that it's perhaps 1,000 psi. And so there are some ideas out there of like rule of thumbs. Okay, just figure it out for a design not to 6,000 psi, but to a fifth of that. Maybe that's going to work out, but there's no guarantee, especially in a thermally driven problem. Okay, so feel free to pause the video and kind of meditate in what I'm talking about. And so, what are the challenges that we've discussed? You can have a weak bond present due to a manufacturing escape, okay? And the inspection techniques that are fairly standard may not be able to detect those. And so that's a problem. And critical flaw sizes may be missed. That's one area we want to hit on. That's a challenge. Bond are not always fully accessible. That could be a problem in a large assembly. You have multiple environments such as moisture and temperature that can significantly impact the strength of the adhesive, and so it's necessary to consider all those parameters in the design of those adhesives. The other point I want to make is that multiple environments here, when I say that, I'm talking about environments within the manufacturing facility as well. As we discussed earlier, moisture can cause corrosion, can cause other issues. Design analysis is challenging due to those stress concentrations I talked about. Those reentrant corners cause a stress concentration. And note how we cannot just take P over A and design the joint as simple as just using that formula, because the peaking is quite complex. For double lap shear, maybe it works a little bit better. We'll show you some of those distributions for double lap shear. But lap shear tests in general can be used to evaluate surface preparation, environmental effects, manufacturing variations, manufacturing defects and anomalies. But it may be difficult to use the data directly to design your joint. And so you want to really, you want to try to anchor, you want to really try to anchor your analysis methods to all the testing you have available to gain confidence in the application of this in the airplane design, okay? So one methodology for achieving robustness, one philosophy. There's just one philosophy that people could use. And the philosophies in this case are based on fracture mechanics, based on the idea of a flaw-tolerant design. And it really levies a building block approach, which I'll discuss a little bit later in the context of the FAA, the Federal Aviation Regulations, relative to fracture mechanics to demonstrate that the structure is robust. We also want to make sure that there's a way to go after those weak bonds. Again, non-destructive evaluation may not be able to find them, those weak bonds, like ultrasound techniques. But then I want to apply some amount of testing so I can determine whether those weak bonds are a problem. And so proof test methodology, the idea behind that, and let me explain what proof test really means, is that, and this is just an example here, say that I have a joint that's going to see 10,000 pounds in flight. The idea of the proof test is to test slightly above that to make sure that any gross workmanship errors are exposed. That's the idea there. And if you can do NDE after, the idea is that the proof test did something if there is a problem to those weak bonds, to open them up or make them more available. Um, and so I want you to pay attention to um, uh, to the methodology I'll be discussing. Okay. So moving forward here, this is one approach to success. It's not the only way, but establishing those process parameters, establish, what are the right surface cleaning agents, the abrasive media used for surface preparation, and the cure cycle. Traceability is required for manufacturing coupon test specimens, subcomponent test specimens, qualification hardware, and production hardware. You can then, after you establish those process parameters, and you do testing to try to hone in at ensuring you have the right parameters, you can then characterize the fracture properties and strength properties. And those testing can include a mode 1 fracture testing, like the double cantilever beam. I will show you how that test data is used. You can use an end notch flexure, which is a mode 2 test. And these fracture toughnesses can then later be used to define critical flaw sizes in your design. You want to make sure these fracture tests do consider the sensitivity to temperature, moisture, geometry, processing parameters, um, 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 okay? And so we want to use this data to determine acceptable flaw sizes. Given the maximum operating loads of an airplane or the aerospace structure, given the finite element model that you have developed, using established critical flaw sizes, we want to make sure that we can come up with flaw sizes that will not propagate to failure catastrophically using these fracture toughnesses that are calculated with step 2. And so you want to determine where to locate them, because at some locations may not matter, but some other locations could matter. For example, let's go back to this joint. The highest stresses are towards the edges of the overlap. If I put a flaw right in the middle, it's unlikely to be a problem. But if I put a flaw right on the edge, the stress is high there, that could be more critical. And so in space applications, we can use factors of safety to protect against this type of issue. And that can be applied to the flaw size itself or to the fracture toughness. I'll show examples later on. We want to identify areas that you cannot have an inspection. And if you don't have an inspection, what can you do? One idea is to just assume there's a flaw in there. I know it's too conservative, but that's just one approach to bound the problem. If you don't have areas you cannot inspect, then perhaps bound the problem. Maybe the right solution there is to really design a structure so you can actually inspect it. I think part of the design should not only be so it's workable, you also want to have a design that can be inspected. And so maybe you have to create some interesting features to allow for that. And so I invite you to look at that carefully. We also want to establish minimum detectable flaw sizes that are capable of catching those critical flaw sizes. And so appropriate non-destructive evaluation techniques can be performed. In the area of expertise, just like when you look at a statistical sample size of strengths when it comes to structural behavior, in the non-destructive arena, we're looking for probability of detection. We want to make sure that we have confidence in the ability to find those flaws. And the sensitivity of inspecting is really limited to a lot of factors. The joint geometry, accessibility, accuracy, how well you can repeat it, and perhaps the surfaces are not really good surfaces to maybe put an ultrasound probe on top of that surface. Whatever it is, you want to increase the confidence in being able to inspect for those critical flaw sizes and the acceptable flaw size in particular. We also want to make sure that the acceptable flaw size can be found. If we define an acceptable flaw size and we say, hey, we can't really inspect for that, then you may want to think about redesigning the joint to the point that that acceptable flaw size can be found. Otherwise, if you have a defect within the joint, it may get missed, and then later could be a problem. Perhaps the proof test is going to help you, but you want to guard against multiple cycles, or perhaps the proof test is not comprehensive. And so, I invite you to think about that and meditate, immerse yourself and try to understand what will happen if a non-destructive evaluation technique during manufacturing missed a critical flaw size. What is the consequence of that? When can I catch that later on? You also don't want to have proof test failures. So part of this is also to guard you against proof test failures. And so, by redesigning the joint to be robust, before going to proof test, if you find a flaw that's a problem, perhaps you can do a repair and you can salvage, you can come up with a mitigation before stepping into proof, perhaps a repair, and then step into proof and be successful. So that's why it's important to connect all these dots together. The processing parameters, the fracture properties, which could depend on the processing parameters. Use the fracture properties to predict the critical flaw sizes, and then determine, can I find these critical flaw sizes? And then design your aircraft or your aerospace structure to be able to be of a robust kind, okay? So let me pause the video, think about. So let's go through this workmanship verification, right? So there's two aspects, the workmanship verification and the design verification. So you have a structural design that was found to be defect tolerant to the limits of detection of the NDI, the non-destructive inspection. The hardware that you're manufacturing is going to follow the same bonding processes as the qualification hardware, the hardware that you're going to qualify. So it is important to make sure that whatever you're manufacturing follows the same process as what you qualify. And then you perform a non-destructive evaluation of the hardware and determine whether the flaws that you found through the non-destructive evaluation are acceptable. And if they're not acceptable, you have to figure out a way of assessing that. Perhaps that's through analysis, testing, or you perhaps do a repair of some kind. But if you're not satisfied with that, if that's not successful, you may have to reject the hardware. Now, you always try to find ways to fix that issue. But if you're able to do that, great. And if your flaw is acceptable, great too. And those two go into a proof test. After that, you go into proof test. Why ND is great? Because if you have a big problem, you can catch it before you fail in proof test and perhaps salvage the structure. Once you go through proof test, check it again. Through non-destructive inspection, check it again. If everything's okay per the defect criteria, go ahead and accept the hardware. If not, if you have flaws or exceeding the criteria, you may have to repair, either look at some additional analysis, testing, see if you can get happy, but you may have to do a reproof, okay? And so that entails that after you repair, you go and do a reproof. but you may have to also, if none of these things work out, reject the hardware, and that's usually your last resort. You want to find ways of making this work if you can. That's really what you want to do, is have methodologies that are robust, so you don't have to get to this point, because that's very disappointing for the whole team. It's disheartening to go through all this effort to only reject the hardware. Okay, so showing that the design is defect tolerant is not sufficient for demonstrating structural reliability, because of those weak bonds that we talked about, right? And contamination issues, manufacturing escapes. So the primary role of NDI is really to determine whether the flaws in the hardware are within acceptable defect criteria, and the proof test is helping pushing those weak bonds to open up. A post-proof NDI should be repeated. Okay, it ensures that the pre-proof flaws did not grow beyond acceptable flaw size, and it can also help determine whether those weak bonds during proof tests open up to the point that could be concerning later on in service. So the primary structure is proof tested. It's important that when you proof test, you adjust the loads to account for test like fly differences. For example, if you test at room temperature, but the adhesive strength decreases by 30% in service at a hotter temperature, then you may want to increase your proof test to account for that difference, or maybe use heating blankets, or use some other approach to account for the test like fly differences. Okay. But the bottom line is that you're trying to uncover these weak bonds that may occur, okay? The design verification is really intended to ensure that you have a good design. Workmanship is checking whether what I built is okay, but design verification is trying to set you up to success. So given a joint, what we want to do is to develop surface preparation techniques. Use them in the characterization of mode 1 and mode 2 fracture testing. Get the maximum surface environments, right? That could be temperature, loads, everything else. Put them into a finite model, determine your acceptable flaw size. And that can vary per region in the structure, no problem. You can do that. In the meanwhile, you also want to develop detectable flaw sizes, and you want to find out what is the minimum that your NDI can do. What is the threshold limits of that? And then it is a good idea to assume that areas you cannot inspect have a flaw, although that's too conservative. But maybe you want to redesign your structure so that you don't have this situation. But once you go into that, what we want to make sure is that the maximum acceptable flaw size that we came up with is detectable by the NDI technique. And if it is, we're in good shape. If not, you may want to think about redesigning the bonded joint with a real purpose of ensuring that no flaw escapes inspection, because if it does, it's going to come and bite you later during proof testing, potentially. Okay. So let's look at federal aviation regulations. Let's look at that perspective, which is different. Okay. And so for that, we go to FAR Part 23, Section 23.573. And the idea here is that we want to make sure that for any bonded joint, the failure of which can result in a catastrophic loss of an airplane, that the limit load capacity should be substantiated by one of these three methods. We want to make sure that maximum these bonds of each bonded joint be consistent with the capability of withstanding the loads, and that's in a different section. And to come up with those loads, you determine that through analysis, test, or both. these bonds of each bonded joint should be greater than this and must be prevented by design features of some kind. It could be redundant bolted joints or something. Or proof testing must be conducted on each production article to ensure that, very similar as we discussed before, it will open up the weak bonds. Or we want to make sure that you have a repeatable, reliable, non-destructive inspection technique to ensure the strength of each joint. What I want to point out is this is substantiated by one of the following methods. Now, what is shown here is a different philosophy from what I discussed before. But it is important to understand that this philosophy can be a little bit less robust, right? Because if you're not exercising those bonds, then you have to really rely on a good NDI, but NDI are not very susceptible to weak bonds. And so what do you do there? So you're looking at process controls, you're looking at training, you're looking at a lot of things to increase confidence, given that you don't have a proof test to check it out. So again, a little bit less robust, but the factors of safety in this arena tend to be higher than the other methodologies I have shown here, okay? These methodologies could use factors of safety as greater as 1.25 per ultimate. In addition to that, the formal guidance comes from 3 documents, and they're called advisory circulars that basically guide the application of these requirements, okay? And so they're given by these 3 here, and we'll focus on the composites one, which is AC 20107B, paragraph 6, and we'll focus on paragraph C specifically because it covers the structural bonding. And so in paragraph 1 of that, it talks about how many bond failures and problems in service are traced back to invalid qualification and insufficient quality control, which is exactly what we covered before. And that physical and chemical tests have to be used to control that surface preparation and to ensure that we do have a good bond, okay? Lab shear, stiffness, and strength testing are really common for mechanical tests and for adhesive and bond process qualifications. But one thing I do want to point out, shear testing may not be as perceptible to these environmental degradation effects. It's been found that peel test has a little bit more appeal to really evaluate that. And so it's going to show you, shear test will show you that those environmental effects, but the peel will be a little bit more pronounced, and so maybe even more reliable from that perspective. Without chemical bonding, you may have that weak bond like I discussed, and so that's an issue. And how you find those things is an issue. So you want to really eliminate any potential for weak bonds, and that really has to rely on process controls and ensuring you have good chemical bonding, that you got rid of all those voids with whatever method you want to do, applying that pressure or maintaining that bond line extra lean. Those are the things that we're talking about here. And so I do want to point out that in paragraph 2, then we go to I apologize there, that the process specifications do need control, okay? And you have to have that process control mentality, which is to make sure you have in-process inspections and tests, and you are checking the quality of those adhesive bonds. The environmental cleanness, the environments and the cleanliness of those facilities is extremely important. We discussed that before. Making sure that adhesives and substrate materials follows a spec requirements. And then that the bonding processes that you use for production and repair meet the tolerances validated through qualification. Again, anything you're doing in the bonding process should be qualified. We discussed that earlier. So when I go to paragraph 3b, what we're looking at is that these options that we talked about do not really supersede the need for qualification of bonding processes and rigorous quality controls for bonding structures. You still have to do those things. And so what we want to really make sure is that if you have a situation where you do have a failure, that there's this fail safety that's going to cover you, right? Like a redundant path for the load. So the fail safety is really implied by the first option that we talked about, the very first option here, of assuming a maximum Dis bond, right? Consistent with the capability to withstand the loads. And so this one here is a fail safety one. You're assuming that the structure has to survive that flaw. So there's the idea of the fail safety, right? To account for these bad bonding processes that could occur. Or you could do that through redundant load paths. That's another approach. If you have redundant load paths, so perhaps you don't need this comprehensive D-bond size approach, or assuming D-bonds is what I meant. I apologize. And so on the other hand, performing static proof tests with limit load, which is the second option, may not detect weak bonds by itself because the environmental exposure over time could degrade the bond and joint strength. Now, this comes straight from the guidance they're providing. But if you don't do this proof test, it may not even open up these weak bonds. But if you were to do them, just keep in mind, you're not really looking at long-term concerns with durability. And the third option that we talked about was NDI, but it is well known that it cannot detect weak bonds at the moment. And so that continues to be a concern. And so again, out of all these three, I'll say a combination of static proof test and NDI really give you a lot of confidence together. To me, if you add the acceptable flaw size as part of this equation, is even more robust, because if you have a weak bond prior to proof test, NDI won't catch it. You go through proof test, it will open that weak bond. And then what you want to make sure is that the flaw size that could open up to, that's within the acceptable limits for in-service application. So that is, to me, very robust. But if you don't have those things, you have to somehow balance that with, extensive training, extensive process controls in situ testing, as we discussed before. So it just becomes a delicate balance that's not always easy to achieve. So let's look at, and I'm sorry for the PowerPoint for jumping back and forth, but we're here now in paragraph 4. Adhesive failures in production require immediate action to identify a root cause, and we discussed the poultry or fish bone. We also discussed adhesive failures in service require immediate action to determine the cause, isolate the aircraft, and then conduct the directed inspection and repairs. And again, these FAA stuff. So environmental considerations, we know that environmental exposure, as discussed before, humidity and temperature, those can degrade the strength of the adhesive. And in addition, the peak temperatures for composite structure installed in close proximity to aircraft systems that generate thermal energy, you need to be able to account for that in your maximum temperature that you're going to use to ensure your joint can survive that, with maybe some uncertainty factor. Something to really look at carefully. And so, again, important to consider environments. So to summarize, I talked about various approaches here, and I want to make sure it's clear in our minds. The approach I was presenting here is ideal, 1 through 6. We want to make sure they have a good approach for workmanship verification, they have a good design that can close, otherwise you're going to have issues during proof testing. And the FAA is looking at a different set of requirements. So it's a little bit different in thinking, but the idea is basically the same. We want to make sure that the bonded joint will perform in service as intended. And so if you don't do proof test, then you have to figure out a way of increasing your confidence in other ways. From my experience working various types of structures, especially for those that are single load path, you really want to pay close attention to not just the design itself, but everything from the supplier, the materials, the in situ testing, the manufacturing processes, and then following that, basically what I talked about, proof testing, and then NDI. Those all things need to go together. And because debonds could happen, maybe FOD is left behind. That is where the acceptance of the flaw size is useful to determine. What is that flaw size that's good enough for my structure? And so going back here, the FAA, in the aerospace industry, we really rely on the building block approach to really get you to be successful. And so that's when I talk about 180 coupons, yes, at this level, 180 coupons. But once you gain that confidence in your analysis inputs, you can start testing less and less with larger types panels or more complicated features until you go to your full-scale test, your qualification testing. And the idea is that once you get to this point, as you increase the level of difficulty of the structures you're analyzing, or sorry, the level of difficulty of the failure modes, the idea is that you are in a situation that you're more likely to succeed than not. Otherwise, if you have failures here, it's costly. You may have to start over. So that's why the building block approach is put together to really, really get you to the end point with a minimal cost impact. And so again, very important consideration. A lot of coupons for very simple testing, and then as I move on, validate analysis along the way. Make sure that each time you validate analysis, the analysis is used in the next level to try to hone in into getting those failure mode predictions correctly. And here you can see it in graphical format. You have lamina properties, coupon testing, lap joints with different bond line thicknesses, surface preparations, anything that can change, that will go here. Then you can start moving to more complicated structures to the right until you actually then test the full scale structure. That's really ultimately what we want to achieve. But now the question becomes, how do I analyze a joint? Because I already showed you the scary part that the P over A did not work out very well. Maybe perhaps I have to use simplistic approaches, but what I want to discuss now is what other approaches we have in our hands. Okay, given a this bond in a structure, given a this bond in this T-type structure, hey, when is this structure going to fail? What is acceptable? How can I define that? It becomes quite complex. And so just want to keep that in mind, that coming up with design analysis approaches is not easy. So anyway, and so I wanna then discuss the idea of how to go about this. You have two approaches. By the way, I am speaking fairly slow, so in this video you can accelerate the video speed to kind of listen to me, but I recommend that you kind of immerse yourself with me, that would be in the same frequency content, if you know what I mean, brain-wise, and kind of learn about what we're discussing here. Pause the video as much as you can to immerse yourself in the different things we're talking about. But there are two different approaches here, okay, that are used in our in the analysis of adhesively bonded joints. And so the thing I want to talk about is that for stress-based approaches, these approaches require finite elements, and typically, and they are closed form solutions. I'll discuss a little bit about that. But when you use finite elements, there is mesh sensitivity, and the mesh sensitivity can be difficult to address. So validating the stress analysis with actual test data is extremely useful. I'll show one such approach, which is one of my favorite approaches I have seen that's worked quite consistently. Now, that's only one approach. There's many others that people use to address a mesh sensitivity concern. Again, because you have a stress singularity, the more you increase the mesh density, that stress at that edge over here, point A and B, is going to keep shooting up. And so how can you rely on that number when it's not clear what it really means, because it's a singular situation, okay? And it requires a good understanding of the stress strain curve. As you saw, it changes quite a bit from temperature to temperature. So it's important to adjust those models to have the correct modulus, because as I showed you before, the stress strain curve does get impacted when you go from cold to hot. In the fracture mechanics approach, it's been known that it tends to be less mesh sensitive. So it's quite mesh insensitive, in other words. It does require fracture testing. I do recommend subcomponent level validation as well, just like with the stress-based methods. And stress singularities tend to be less of an issue, because you're accounting for that. You're accounting for that length scale effect in a different way. So the fracture energies, I'll be discussing that more, and you're able to hone in into the critical parameters driving failure. So for stress-based methods, typically to address mesh sensitivity, you're looking at a critical distance from the edge. With fracture mechanics, you're looking more at an energy-based approach. So especially for composite adherence, my recommendation is to anchor your models. The surface preparation, manufacturing techniques, the range of design variables we talked about, such as thickness, environments, and a full understanding of all the failure modes that you may encounter. Otherwise, there might be an issue there in not really coming up with a design that works out. Secondly, there's a lot of value in that if you have a flight feature that's quite complex, there's value in doing a subscale test that envelopes the environments you see in the flight test configuration. So it's cheaper, right? But you want to make sure that it's apples to apples. Because if you have a completely different configuration in your subscale test, how do you have tests like you fly? You don't have that. So it's important to keep that in mind along the way. So I do invite you to go in the literature. I think it's important. If you're going to work as an expert in adhesively bonded joints, it's important that you go and try to understand what Hart Smith was doing, the approaches that the Air Force had, the McDonnell Douglas had, Southwest Research, the University of Delaware, Lockheed, the Navy. There are these codes out there, okay? There are these codes out there. There's a lot of literature behind it. It's great to kind of study how things have evolved. And you're going to see that approaches have evolved a little bit from the strength side to the fracture side. But the strength perspective continues to be heavily used and should be considered in your evaluations. I invite you to find this report. and it's by Naveen Rastogi, and it really goes into these types of methods. Okay, so let's start with the very early methods in the early 1900s. This is not a new analysis. Okay, Volkerson model is the very first model where the adherents were assumed to be fairly stiff. And so all the deformation was coming from the adhesive itself, and they called it a simple shear lag model because it can only transfer shear. In that model, the adherents are assumed in tension, and the adhesive is in shear only. And so and it's also assumed they're constant across the thickness. So that is it. Later on, Golland and Reisner, I invite you to read that paper. Great paper. It describes how the analysis approach evolved from Volkerson to something that's even used today. If you ran finite elements, I have high confidence that your finite elements are going to match fairly well with Golland and Reisner. Not perfectly, but good enough. I may show you that later if we get the chance. But it is well known for the classical treatment of single lap joints. This model assumes that the transverse normal strain and the shear strain in the adherents are small compared to what's going on in the adhesive layer. And the deformation of the adherents due to the bending effect, it is taken into account where the adhesive layer, we are looking at basically a continuous distribution of springs that are positioned between the adherents and accounts for shear and peel both together. As I told you before, when you pull a single lap joint, you expect a contribution of shear and peel. Here's really what I want to show you is that when you pull a lap joint like this, the Golden and Reisner model is capable of giving you a shear stress, which is this one right here, and the peel stress is able to give you that. And keep that in mind, the effects are much more pronounced towards the edges of that adhesive, okay? So very important to understand because it is quite powerful to really study the theory behind it. So the Volkerson model actually was used very frequently to predict failure, using something like the maximum shear stress or maximum shear strain criteria. But over time, people have questioned that because what does it really mean when you have a singularity at that reentrant corner in a single lap joint? What does that really mean? And so you can use a representative single lap or double lap joint test data as an alternate approach. So you test a representative single lap or double lap, and you'll calculate the average shear stress at failure and use the peak shear stresses at the extremities of the adhesive bond line from the shear lag model. So you'll have those. And this value of the peak shear stress is then used as a design allowable for the actual joint design. And so a prediction of for the average shear stress at failure can be estimated for the hardware design from that perspective. This represents really a first level analysis and is limited into what you can really do with this. But it is a first level analysis. I'm going to discuss something a little more advanced here, maybe not too advanced, but I think simple enough to implement, and is one of my favorite papers in the literature. This was pointed to me by a very close friend of mine. His name is Eric. If you're listening to this, thank you for bringing this paper to my attention. Ever since I saw this paper, I've seen it referenced many more times after that. Now, I like this paper because of the simplicity in the way to explain things, but this is not completely new, right? The approach I'll be discussing is really based on the critical distance approach. The gentleman in this paper looked at it a little bit differently, but they still look at it, they come up with this critical distance approach. what is the idea behind it is that I cannot trust the peak stresses at the edges, but perhaps I can start trusting what's going on in the interior of the adhesive, not towards the center, closer to the edge, but not quite at the edge. And so what they did, they modeled the adhesive very well. So they measured very well. You can see that here. They modeled the adherence, the adhesive, and they track stress and strain along the center line, along this bond line length. So they're tracking how those behave. And and they called it the critical longitudinal strain approach. But just call it critical distance approach. I'm okay with that. And this is not new. It came back even from Taylor in 2008. So I invite you to read the paper, pull this Taylor reference, read that. But even Taylor will reference even papers that precede that. So it's worth kind of looking at those. According to the CLS approach, this critical distance approach, failure occurs when the longitudinal strain along the adhesive midplane reaches a critical value at a specified critical distance. In other words, at a particular distance from the edge, at a particular value. And the question is how to find that distance and how to find that value. So the approach by these authors was basically, hey, test two single lap joints with the same geometry, except with different overlap lengths. Same manufacturing process, everything should follow the same. And you want to test that to failure. That was the point they're trying to make. And this is just a simple 2D linear elastic finite element analysis of these two joints. You're going to analyze these two tests. And then next, what you're going to do is plot the distribution of strain along the adhesive midplane for both of these situations. And the intersection of these two plots for these two single lap joints is used to come up with this critical distance and this critical value. As an example, here is what they did. So they plotted the two single lap joints with two different overlap lengths, and the overlap lengths in this case is 8 and 15 millimeters. The thickness the same, the adherence the same, everything else the same. And they plotted that strain along the adhesive, the longitudinal strain, and the location at which these two curves intersected is the point at which they call critical point. And in this case, it was at a distance of 0.07, okay? 0.07 in the normalized configuration. And the critical strain was calculated as shown here. So with this normalized value, you can now apply it to any overlap length. And then this critical strain is used as a value moving forward. Using this approach, the authors went and tested a wide range of joints, overlap configurations, and different overlaps, different thickness, adhesive. And they used this configuration for their single lap joint. Again, metal and metal, so not composite. Composite will add another complication, which is the failure mode of the first ply failure within the composite. So I do want to point out that the authors demonstrated great consistency between experimental data, the testing data, which is in blue dark, and they showed that the predictions with the critical distance approach are doing great, fabulous. I'll call this fabulous. And it's not perfect at times, but it's within reason. Okay. The other thing I want to point out is when you look at these joints, joint A, the overlap length is increasing. So let's look at that. For the same thickness, overlap length increasing from 8 to 60. So we track the A1, A2, A3, A4. You can see here the overlap is increasing, and the overlap increased, the failure load also increased. So clearly the overlap length increasing that gives you good performance. No question about that. But the thing I want to point out is that I went from the overlap length of 8 to 60. That's 7 times more. Question is, did that increase the failure load 7 times more from A1 to A4? And clearly not. I got about 3.5 or so, not 7. So you could perhaps use this as a design guideline, as a starting point. You can see that for thicker adhesive, you also have going from B2, B3, and so forth. So you're seeing there's an increase in capability with overlap length, and that trend seems to hold for all thicknesses. However, for the same overlap length, if I keep that constant, what you find is that increasing the adhesive thickness does decrease the failure load. You have more opportunities for weaknesses within the adhesive that should be looked at carefully. So I encourage you to kind of look at that more as we discuss it. So why don't feel free to pause the video or maybe even backtrack and go forward and kind of study and come up with some conclusions of your own, so that you have a better understanding of what the trends are. But I think the trends are great, and they do show a lot into what's going on. And this is again showing that with adhesive thickness, the failure load does decrease, increasing the importance of controlling bond line thickness. That is the goal. Okay, that is the goal. But not making it zero thickness, because then there's a gap, and I don't think you want that in your designs. So another way to look at this problem is using fracture mechanics, and this is a little bit more top level. So I'm not going to go into the theory of fracture mechanics per se, because there'll be a lecture on that in the future. But I have to cover fracture mechanics as it relates to adhesively bonded joints, because it does play a big role in the coming up with these acceptable flaw sizes and even size and designs. And so it is worth looking at this approach to some level. And so the fracture mechanics approach captures the physics for the most part, delaminations, disbonds, things like that. You can put you can look at flaws at different interfaces. But what it like in strength mechanics, stress or strain is the driving metric. But in fracture mechanics, I'll introduce a new metric. It's called the energy release rate, and that's really the crack driving force. And what is that? Basically, that's the energy that is released from debond growth. If I apply loading and the energy release rate is small, then the crack may not grow. But if it reaches a critical value and there's enough crack driving force, then that crack could propagate. And that crack propagation is really going to cause energy to be released, because anytime you have to form new surfaces, which is what cracking is, energy has to go into that. And so the energy then has to be released by the structure in some way, so that energy can go into the formation of the cracks. This is based on Griffith crack theory. So again, I invite you to pause the video, Wikipedia Griffith crack theory. I'll go through that in the future in more detail, but I think it's worth kind of stopping now and kind of taking a break. But the debond will grow when the energy release rate reaches this critical value. And so that's very important. This critical value, fracture toughness for this adhesive, can depend on temperature, moisture, is material dependent, and sometimes can depend on the geometry of what's going on. So many people claim is a parameter that's independent of geometry. I say it is for the most part, but there are some dependencies that need to be looked at, especially when it comes to mode mixity. And I'll cover that coming up. To address fracture mechanics, the mode 1 testing is an approach that can be used. Here, the coupon STM 5528 was used, but you basically really want to follow the STM standards that we discussed before. In this case, a face sheet and doubler were put together. You could have a film adhesive in between, and in this case, this standard was used to measure the mode 1 fracture toughness, this GC value. I'll cover how to get this G value later. And so you want to compare, you apply loading to the structure, compare this G to this GC, and if G gets close to GC, then that's when you know that I'm close to fracturing the structure. And the fracture can be unstable or stable. There are situations it's okay, the crack growth is growing in a stable manner. It could even potentially arrest itself and not be of any other issue. Fracture methodology, one way to calculate this energy release rate is using something called the virtual crack closure technique. The virtual crack closure technique, sorry about that. So again, going back, the strain energy release rate is the energy dissipated during fracture per newly created fracture surface area. So how much energy got dissipated per fracture surface area, and the flow will actually really propagate when this G value equals GC or exceeds GC. So GC is material dependence, as I discussed, but it can actually depend on the manufacturing processes and surface preparation techniques too, which makes all this more fun, as you saw so far. Perhaps at the end of this lecture, you may think 3 or 4 times, do I really want to adopt bonded joints? I'm not going to answer the question for you, because I think my role is to educate you about the advantage and disadvantage of each approach and let you decide for yourself what makes sense for you. But I've already shown you that the bolted joint designs are heavy, but less baggage. The adhesively bonded joints lighter, but a lot of work needs to be done. So there are 2 methods in the literature, 3 methods even: virtual crack closure technique, decohesion zone models. So I have the paper in slide 2. So if you backtrack all the way back to slide 2, I have a paper written on this subject that uses that to predict adhesively bonded joint failure loads. Very successful, as you will see in that paper. And then the other approach is XFEM. So 3 approaches. I'll be focusing on VCCT. The decohesion zone model is the one presented here. But again, I really want you to go to that paper and read that if you want to learn more about this technique. Abacus and many other software have adopted this. Is in essence a Goland and Reisner approach, but glorified. You have a bunch of springs that are continuous. They're acting tangentially to prevent sliding, and they're acting in this direction normal to prevent peel. But the difference is that these springs can actually break, while the ones in Goland and Reisner cannot break. These ones can break, and they follow a constitutive law. And the constitutive law is put together in such a manner that when the spring breaks, the energy under the curve is equal to the critical energy release rate. So it's a very clever method, but it has its disadvantages. It's not easy to extract G1, G2, and G3, and then maybe write fracture, margins of safety. Numerical convergence can be a problem. And if you have cracked the kinks or you have other types of situations, this could be a challenge, this particular approach, which I worked on this. This is one of my areas of expertise, but I'm trying to be honest with you that it does represent some challenges. Now, if you go to the literature, and again, you pause right now and go to Wiki or Google, you're going to find plenty of papers using decohesive or cohesive elements to predict failure of adhesively bonded joints. But I think you're going to find that it is challenging to apply. But it's doable, and the softwares today have it. Okay, and I invite you to read the paper I wrote in that second slide. Um, the fracture methodology I'll be focusing on today is the virtual crack closure technique because it's really close to the fundamentals of fracture. There's a great reading I recommend is VCT History, Approach, and Applications by Ronald Kruger, very renowned in this area. And the technique is really based on the Irwin's crack closure integral. That sounds like a mouthful, but it is based on that. And the assumption here is that the virtual crack extension has minimal effects on the crack front and stress strain. Okay. Now, many people confuse this approach um, with the crack closure method. They're very similar in what you're trying to achieve. Okay. Even though virtual crack closure technique is what we're talking about, I think it's important to differentiate that with the crack closure method, or we call it the two-step crack closure technique in the literature. This terminology in the literature, you're going to find them mix it up with the VCCT, and that's inexact, but they're trying to really achieve very similar things. And the idea here is that you're physically extending the crack in two different finite element analyses. So you have a crack, you run another one with an extended crack size, and then you use the crack closure method based on Irwin's approach. And you calculate basically the energy released by extending that crack to one to close the crack. And so I won't go into the details of that, but in essence, you're able to then determine the energy released, okay, due to that crack extension. The visual crack closure technique achieves the same idea of calculating these energy release rates that we talked about. Now, don't lose the perspective here. What we're really talking about is that the fundamental parameter in fracture mechanics that allows you to predict delamination growth or debond growth is energy release rate, the strain energy release rate. And so if the load is small, then the energy is small. But if the load is sufficient, then the energy release rate will reach a critical value, at which point the crack would propagate. And so that's very important for us to consider. The virtual crack closure method is based on the same assumptions as the crack closure method. But you can do the whole analysis at once, okay? That's the idea. You can do the whole analysis at once. I'll let you read this recommended reading. But the idea is that you're looking at the crack tip located ahead and behind the crack tip, and you're looking at calculating the energy release rate based on the forces required to close that crack that you extended virtually. And so this uses force information and deflections ahead of the crack tip. The forces at the crack tip and deflections ahead of the crack tip to inform what the energy release rate is. And the total energy release rate is really what I want to compare to the critical value. And so Hypersizer has great capability that I invite you to look at. Is based on non-finite elements formulations. There's a great paper by one of the founders of Hypersizer, but by NASA, and it looks at using Hypersizer to come up with this analyzing this using the virtual crack closure technique to get the energy release rates. So I invite you to look at that. And so you can curl, you know, my point here is these two approaches should be fairly similar, the VCCT and the cohesive elements. Um, and this is an example of double cantilever beam. And if you were to use VCCT or this decohesive model, which is a paper I wrote in that slide too, versus the VCCT, which has been worked on by many people, including you'll find papers by Dr. Klug. Um, he works in my same area of expertise, one of my mentors. Thank you so much for everything you've done for me, Klug. Um, but it worked. These two things tend to compare well, and I hope you can go and study that a little bit. The energy release rate using VCCT, we've created a YouTube video with a TA on how to apply VCCT for a single lap bonded tube. And in your, I'm going to give you homework. So this lecture does not come with free time spent at home, but this is for you to work through an example. So I'm going to ask you that you run this exact example to see how VCCT can be used in Abacus to come up with these energy release rates. And the idea is to predict the failure of these joints. And so I'm not going to go into the specifics on how Abacus is run, because that's done in this particular YouTube video. Okay, and I'll make sure that I include a link of this YouTube video at the bottom of this video. So feel free, at this point in time, feel free to pause the video here, go to that YouTube link, watch it completely so you can learn how that's done, and then come back here. That's a good approach of breaking up your time. But let's look at an application of something that a colleague of mine, he patented this he patented this with another organization, but his name is Eric Lundgren, and you can find his patent. But this is called a double. It's basically a redundant joint, a durable redundant joint, because you have this piece inside, right? These two pieces are separated. So think of this joint as splicing everything together. So you have the outer doubler, which acts like a splice that connects the two sides. But now you have this interior box here that also does the same thing. So if you were to have a flaw in any of these locations, then the hope is that this is a more robust design, because other areas are better bonded, will help you. Now, we don't want to make the mistake of people thinking that because you have redundancy, you can be less careful. We learned that from the Challenger investigation. I know this is not O-rings, but hey, if a design is bad for the primary O-ring, and I discussed that in the previous lecture on bolted joints, if the design is bad for one O-ring, then it's probably bad for the second O-ring. And so you may have redundancy, but perhaps you've screwed up the whole design thinking that you have redundancy, but the thing came apart easily. Just think that you need to pay attention to that aspect in a design. Don't think you have redundancy, but the design or the manufacturing process is not good enough to the point that the redundancy you think you had or you thought you had, it's not there. It stinks. That will stink. So if you were to put a flaw here at the very top and a little flaw here, we could calculate the energy release rate using the procedures in the other YouTube video, and you can get G1 and G2. In this scenario, you have a mixed mode condition. You get some amount of mode 1, some amount of mode 2. And the ideal scenario is to take mode 1 and mode 2, add them up, and compare the total energy release rate, to the critical energy release rate. But the problem is that it's well known that under mode 1, the critical energy release rate is smaller. if I do a mode 2 test, the ENF, the end notch flexure, the critical energy release rate for that is at least twice. So what do you compare this G total to the G1C or G2C? One approach, if you want to be conservative and want to keep it simple in the design, take G1 and G2, add them up, and G3, because you also have sliding into the page, potentially, not in this example, but you'll take G1 plus G2 plus G3, calculate the total energy release rate, and compare that to the mode 1 double cantilever beam fracture toughness G1C. That's one approach. That will simplify everything. But if you don't want to be too conservative and be more realistic, then it becomes a little more tricky. And why I say that? Well, there is an interaction of G1 and G2. There's a failure criteria, and one criteria people use is called the power criteria. And the question is, if I'm more mode 1, I should be, the critical energy release rate should be closer to the G1C. If the mode is like sliding mode only, then I expect DGC to be more like G2C. The question is how I compare this G total to GC. That's not entirely clear, but we know that there's a relationship where a power law could be followed, and when this is equal to 1, fracture occurs. The complication is, and by the way, G2C tends to be about twice of G1C at a minimum. It could be less, but usually that's a value. I recommend doing the test to confirm it for yourself. But if you don't have the data, twice G1C is a good idea. For actual design, I recommend doing the testing. It's not that hard. It's a 3-point bend test, basically. You can see that here. With a flaw here, I recommend the flaw to be about 35 to 37% of the total length. If you find my thesis online, I explain why that is. There's a closed form solution that explains where the 35 to 37% come from. And it comes from making sure that this flaw doesn't go unstable to the point that you cannot even acquire any data whatsoever. So that's why you want to keep the flaw to some length. Otherwise, you're going to have some issues with the test. But the G1C out of this test will be smaller than the G2C. And the question is, when I add G1 and G2, which I get G total, which one I compare to? And plus I have this power law criteria. Well, let me show you one approach that you could use to approach this question. And I hope at this point you're not bored. You can take a break, maybe go to YouTube, check out some people must have tested this stuff in YouTube. So check it out and kind of learn how that test works. Come back to this. I know that there's a lot of information here, and it's probably you're getting a little bit tired, but keep pushing along through this YouTube lecture, and I'll really appreciate that if you did that. So we would like to know when D-bond propagates, and I wrote this by hand just for fun because it's kind of fun to see handwritten stuff. So we would like to know when D-bond propagates. This should occur when the G totals equals GC. And so if you were to have a mixed mode condition, don't you agree there's a particular value of G1 and a particular value of G2 that will reach its own critical values, and at that point, that should be equal to GC. So in other words, G1 plus G2 equals GC, and when that happens, fracture property is fine. No question about that. But we can also say that there's a value of G1 that's critical and a value of G2 that's critical that when added together gives you this critical energy release rate. Now, to make sure you understand this G1C, this G1 with superscript C is not the G1C that you measure from mode 1 testing. This is something we're going to try to calculate. And so what we want to do then is take the ratio of G2 and G1, and we call that the mode mixity. So if everything is mode 1, M is 0. If everything is mode 2, then this will be infinity. So this is what we got. If I use a power law criteria, when this is true and is equal to 1, I say the criteria is satisfied. And that occurs for a particular value of G1 and a particular value of G2. And notice how the denominators have the critical energy release rates that come from testing. G1C and G2C come from testing. And G1 superscript C and G2 superscript C come from, that's what we're trying to determine, is what does that look like? And so we solve for G1C out of this equation. And I know what the ratio of G2 to G1 is because that information can be found from the finite element modeling, for example. Here, I can plot the mode 1 counterplot and the mode 2 counterplot and then take the ratio of the two. Now, in the YouTube video, here, we show you how to do that, okay? So you know M, so you know M, and so if you know M, you can calculate G1C. Once you know G1C, you can plug it back into this equation, and you can calculate GC, the critical value, the critical energy release rate that has been adjusted for the mode mixity. Now, if everything was G1, then I expect that G1 should be equal to, this G1 value will reach G1C. But if everything is mode 2, then I expect this to be G2C. Okay, this critical energy release rate will become G2C for mode 2. This critical energy release rate will become G1C. And for mode mixity, it's going to be somewhere in between. We just don't know until we use this power criterion, and then we calculate that mode mixity, which can be found through the calculation I just mentioned. So GC then becomes this formula. M is a mode mixity. And what we want to do is compare this GC to the total G value. Now, if you don't want to go through any of this, make it simple. Take the total energy release rate and compare it to G1C. And that should be conservative for what you're trying to do. So moving on forward, using this method, and when Eric and I worked on this problem, there's a paper published about this at several conferences. But you're going to say that I faked these results, but it was within 8 pounds of the test, and we did not really monkey around with the properties. I think it was serendipity. If you were to ask me, the testing had almost no scatter, and that was actually surprising. The whole thing was surprising. Bottom line is, these methods tend to work, but they won't work if you start monkeying around with the surface prep. You start, you don't consider things that should have been considered as discussed before. For design, I recommend using a factor safety of 2. You can apply that to a calculation like this. So you have G1, G2, plug it into this formula here. The mode mixity is easily calculable. You know, you can calculate that. And then you can calculate margin of safety. We want to make sure the margin of safety is greater than 0. So why don't pause the video, study this equation. This GC came from this formula that derived here. Spend some time studying this and see if it makes sense to you. And so as an example, if everything is G1, so there's no G2, so I have G1, M is 0 for pure G1. I'm sorry. Yes, for G2 0, M for G2 is 0, M is 0. So you can see here, this goes away, this goes away, and so the G1 gets compared to G1C. So check that out. Work through some problems here. I recommend a factor safety of 2 for this type of calculation, but this is program dependent. You know, so FAA could have a different requirement depending upon who you're working with. Nuclear industry could be different. I don't know. You have to look at the requirements for your program. But factor of 2 sounds reasonable, especially for the critical energy release rates that you plug in here are average values from the testing. If G1C and G2C already accounts for some sort of statistics, then perhaps this 2.0 doesn't have to be 2.0, and perhaps you can use a lower factor safety. But the factor safety is there also to protect you against assumptions you do in your analysis or errors. Like nobody's perfect. And putting a factor safety of 1.0 here can be quite cavalier. It's like saying, "Oh, I know exactly what's going to happen. I got it right, 100% the right, time." Think about that for a minute, okay? And you often confront product managers that want to see if you can get lower here to get a positive margin. Look at things carefully, and maybe you can be flexible, but not always. As long as you maintain integrity, technical integrity into what you're doing, we should be fine. The minute you start compromising that technical integrity to schedule pressure or somebody's opinion that's not based on anything, I start worrying. But again, factor of two is a recommendation, and so it can be considered. So here's an example of how to come up with acceptable flaw size. You can calculate the margin, increase the flaw size. So say I have this flaw here. I increase the flaw size until the margin of safety crosses 0. And at that point, I can call the acceptable flaw size. As long as the margin calculation had the factor of safety, I should be okay. I don't recommend going right to 0, right? Leave a pocket margin of 10% for non-conformances or something like that. Bottom line, make sure this flaw size I came up with acceptable can be inspected. If you can't inspect that, you start getting worried that I could miss something in my design. A third application, which is covered in one of the papers I worked on with Eric, has to do with secondary bonds. And so here's an example of a structure, 100 Gs, 100 Gs, and it's a 5-pound secondary structure. The question is, can this come off? So you can assume a flaw size and kind of do sensitivity studies and see, okay, if half of these things is not bonded, do I have a problem? And so you can then study the problem. Here you can see that G2 is almost 0 for this example, which is quite interesting. There's a 100G lateral, 100G that way, but the reason is that the 100G is acting like a moment, which acts like a peel. So it is mode 1, basically. Notice if I put a 1-inch flaw right in the middle of the sample, not at the edges, G1 is close to 0. But an edge flaw, you can see here, is quite significant. Another interesting fact is a 1/4 of an inch flaw in this example didn't increase your G1 by a lot, which tells you that for this example, you're not too sensitive to the flaw size, and makes you think that in this case, you probably have a pretty robust problem where fracture is probably not a concern. If this was a very critical piece, probably a proof testing just to check out the gross workmanship of that bond line. But it looks like in this example, you could be fairly okay. It's hard to tell. You can use edge feelers, by the way, after you bond things to see if there's any edge cracks. That's one way. Inspection with 10x magnification. Looking for anything that looks weird. Not a bad idea, especially if you cannot inspect it. So let me move into design best practices. I went from philosophies, things like that, to design best practices. It is a good idea to apply adjacent to the adhesive and stacking sequence of the laminate to be 0 degrees because that's aligned with the direction of the load, and it will help reduce that stress concentration. If you have something that's not 0 degrees, then you're going to have a more pronounced stress concentration. A stiff substrate in general will reduce the local bending in that reentrant corner, and then as a consequence, reduce that stress concentration. Using tapers in adherence can also reduce the stress concentration, and it sounds a little bit contradictory, and that's why all this is a balance of design sensitivities and things like that. But using a taper can also reduce that stress concentration. The longer the taper, the stress concentration can get reduced. The use of a joggle flat joint, and you may say, what is that? Well, good time to pause the video, go to Wiki, go to Google, study what that looks like. but that can also reduce stress concentration due to the reduced load eccentricity. The idea is to reduce the eccentricity in the load that we saw in a single lap joint. Anytime you can do that, you're moving in the right direction. The problem is that how you manufacture a good double lap joint. That's not easy. Increasing in lap joint overlap length increases joint strength. If that you have a ductile adhesive, well, for brittle adhesives, you know, the increase in overlap length is not going to be helpful. Okay. Overlap length can influence the failure modes. Perhaps you shift the failure mode into the composite. Thicker adhesives can result in an apparent shear strength decrease, as I showed before. So be cognizant of that. Some people put nice fillets to reduce the stress concentrations. You can see that here. These are kind of poor designs. Be careful. You can see here some taper ideas to reduce the stress concentrations that you may encounter. And these are very successful approaches to dealing with these stress concentrations of these reentrant corners. Here are some do and don'ts from the literature. You know, this is a good, you know, do. This probably a don't because of the load eccentricity. Here's one where you have kind of a locking mechanism. That's better than having this, but this is probably harder to manufacture. This is a good do, but if you put it like that, then now you have this prying action. Now, I'm not saying don't use this. Try to lean more towards the left one if you can. This is a horrible idea. Prying action. Hey, go ahead and put a splice to kind of distribute that load better across that two connections. Other ideas are shown here. Butt splices can be dangerous, but then these ones with the overlap are great ideas. Here's an example of a do and a don't. This will produce less stresses in these bond lines compared to this one. Okay, and I think you should do an analysis, finite element analysis. Maybe that could be a good project for us to study. When you have a shaft type thing, like something bonded in this manner, try to have a nice footprint that grabs onto the structure. A pillar with something that grabs onto the structure that gives you good area. Try to make it inspectable if you can, but if not, then you may have to rely on proof testing, a lot of process controls, and making sure you are confident about what you're doing. I want to compare the double to single lap joint again, and just very simply, you can see here that the single lap joint, the shear and the peel both get dropped significantly. And this came from this paper. I invite you to look at that. That clearly shows that double lap has almost no eccentricity, so you're a little bit in better shape there. So I recommend looking into that because that's very good to consider. I told you if I had time, I'll go through the Golan and Reisner solution. You can see here the peel is greater. You have peel and shear for a single lap joint. Finite elements shows you that for the double lap, check it out. The stresses drop. Golan and Reisner look very nice compared to FEA, but that's not the point of this chart, although I think you can look at that too. The point is that FEA compares well with Volkerson model. FEA compares very well for Volkerson model for double lap joint. For single lap, you don't want to really use Volkerson because it was not really meant for that. The Golan Reisner solution is a better approach. And you can see here, that's not too shabby. The comparisons are not too bad. And here's additional comparisons you can look at. Bottom line is, double lap joint cuts the stresses by half compared to single lap joint. And here is an illustration from the Composite Materials Handbook and also in other papers like FAA. Bottom line is the strength increases. The strength increases with these various configurations as you move up. And the failure modes change. You can go from peel and then shear and so forth. So I invite you to take a look at this. Anytime you can go with a better bonded joint design that's less sensitive to manufacturing imperfections, why not, right? But that is not always easy